Well, hello. My name is Sjors de Wit. I am a co-founder of Jitter. We do embedded stuff, not only the software stuff, but also a lot of different hardware things. We're doing this for the last 7-8 years. I just wanted to give you a few examples of what we worked on. The leftmost, the Fogwatch, is one of our first projects that we worked on. It is used to monitor vibrations at construction sites. So, well, let's say they are doing some construction work and they are working too hard. You know, you want to be safe that the surrounding buildings are still alive after that. More on the right is an example of one of the hardware boards I designed, and yeah, well, guess what is the render and what is the real product. In the middle, I thought it was fun to include this. Some people may recognize this. The photo was taken at the TU Delft here. A few years ago, there was, well, the corona pandemic, and the TU Delft had an initiative to build a pandemic ventilator for that. We basically developed the electronics on it and also the firmware running on the ventilator. These were all interesting, but they were written in C, so yeah. What we are doing now, well, besides rewriting some of the previous projects in Rust now, we are working together with Dozer, a company in Leiden, on a 3D printer, and it's not just a printer, it prints personalized medicine. The idea is, let's say, you can choose between 1 pill or 2 pills, but maybe your perfect dose is 1.3 pills. So that's what this machine can do. And in the future, you may even be able to combine multiple pills in one. So instead of sorting out your daily routine, especially with older people, they can have 1 pill every day and that's it. Just a bit of overview of what is in this machine. A lot of different modules, most of them run embedded Rust in a no SCD environment without memory allocation, and on our own custom hardware. So basically all of these blocks are different hardware modules, and all of the green blocks, they run Rust. So most of the machine, and of course the blocks that do not run Rust, well, we have some issues with them. About state machines, this talk is going to maybe complement a bit what Dion talked about earlier. Embassy is mostly about how do I avoid manually managing state. This talk is about what if you do want to do that. Some Rust code. I'd like to start with this because it does not appear to be a state machine. You have a struct with 2 variables, a position and a flag. Did we reach this position? This assumes that the update function is just continuously pulled, and eventually the target position is reached and it has nothing to do anymore. Now, of course, the set target position, we had a bug in it. We needed to update the other flag. What is the issue here? We have 2 variables and they are actually not independent. You can basically express this code as a state machine on the right, where I've just put it in a match statement and written all 4 combinations of these 4 variables. And you see one of those combinations, the second, does not even express a state that should be possible. So why can we? What can we do? We can basically convert this struct to an enum, and in Rust you can put values in an enum. Now suddenly, although it looks like a bit more code, remember the previous slide we had 4 states, now we have 3, and they are even describing better what we are doing. Because now we have a position, but you always know, is it that we are moving towards this position, or have we reached this position? You cannot access a position without knowing what it was for, because you need to parse this enum. This is how handling that state looks. Basically 2 states, well, you don't have to do something. This is basically the same code as what we started with. Of course, now you know that in the second case, you have reached a position and you could trigger some event on that. Well, the last part is basically the old code, and the only thing we now do is set the state to position reached. Of course, you can still have a bug and forget to set the state, or maybe you accidentally set the state to the wrong state. So this is why it's important to really think about how is your state machine going to be structured. And in my experience, the better you do it, the more reliable your product will be. Of course, in embedded, lots of the time you're not allowed to just reboot the computer because your system is built away in the ceiling, or it is a 200-kilometer drive. So you really want it to stay up for a long time. Also, my experience, I've developed a lot of C code, and in C code, writing a state machine, it's no one's hobby. Everyone is a bit scared of it. And why is it? Well, you have the big switch case, and sometimes you add a new state and you forget to handle it somewhere, and it appears to run fine until it doesn't. In Rust, actually, it can be a joy to implement it. The match statement is much more powerful than switch case or what most languages have. And well, even the compiler can help you even more. I'll look into it in the further slides. One thing you can do is actually express state even more into like specific types that are only allowed to be converted into some other type, but I'll come back to that later. The end goal of what you want to reach is to have really big confidence about your machine, right? That your drone is not going to crash, or at least that you know under which conditions it will, and that it will crash in the most safe way that it can. Or in the case of a medical 3D printer, there are maybe cases where it makes a mistake, and that is okay as long as you really, really know, like the operator can see something went wrong, please clean the machine, throw this all out, is wrong. That's okay. Okay, a slightly more explicit state machine. I think most of you recognize this. The trick is that there's a few state transitions and you want to guarantee that only those state transitions are possible. So let's say you have a printer, you can go from idle to printing, and you can go from printing to idle, but you cannot go from error to printing. So once something has gone wrong, you don't want the machine to suddenly start moving erratically or moving as if it was printing something, but it was not actually printing something. One useful technique for this is going one step further. You have an enable state. You also have events. Then you can have quite a complicated code if you want that handles the state machine and triggers, like you can have a lot of code that handles the idle state, and sometimes it says, okay, nothing happened. Okay, sometimes I need to throw an error. And then on a completely different location, but in one location, you can handle all state transitions. You basically match on the existing state and on an event. And for a complicated state machine, this can be a long list, but it's an easy to read list, and it's easy to explain even to non-Rust people. You can just walk along and say, okay, in the idle state, nothing happens, it goes to idle. Do we want that? Okay, nice. Well, etc. You can go on. If you think it's going to be too long, you can use wildcards. For example, here we say basically whatever the state is, if the event is error, we just go to the error state. And if we're in the error state, no matter the event, you're stuck there. Of course, it depends on your application if you really want that. Maybe you want to way out of the state, out of the error state, but at least not uncontrolled. Okay, I have already kind of introduced this, but I'm not sure if people are familiar with the type state pattern in Rust. You may have seen it in the builder pattern, where you basically say you have a printer builder, and what you can do with it is say build, and then it emits a printer. And that's the only way to get a printer. You cannot say manually create this object. That's what we've done here. We have a printer struct, but we have, well, for now it's dummy, but it's a private property. So manually constructing a printer, it won't work. The only way to construct this printer struct is to first have an idle printer, called start printing, and from that you will receive a printer. This can be very helpful in building a state machine where you really want to be sure that some state can only be reached in a very controlled order. So this is what it would look like. You have an enum state. Again, we use the property that you can store data in an enum. For example, the idle state has an idle printer. The printing state has a printer. Okay, maybe these names are not the best. And the error state, you see, it has nothing. Now, the interesting thing is that what we implement on state is a function that does not consume, that it consumes for itself. There's no reference here. So once you call next, your original object is gone. So imagine that in this printing object, you have also the ownership of your peripheral drivers and basically everything you need to physically start moving a machine. Once you have reached the error state, as we highlighted here, the compiler will yell, or depending on how you interpret it, nicely remind you that it is not possible to create a state printing object. Why? Because you need a printer. Can you access the dummy? No, because it's private. So the only way is here in the idle state. There you have an idle printer. So there you can say, I want to start printing. So, well, of course, it's a very simple example. Like the only implementation in printing is say, oops, something went wrong and we go to error. But I hope you get the idea. Yeah, so basically all of this, with all of this, I want to say, like, in a lot of embedded application, it's really important to be very confident about how your machine is going to behave. So, of course, it's nice that it's satisfying to implement, or, well, actually, that is my opinion. I mean, if you don't like state machines, maybe you should use Embassy and, like, let the compiler and the framework handle all of this. But in the end, it is always a trade-off. Which pattern suits you? Like the very simple match statement, oftentimes it's enough. I've used it a lot. Like simple device driver, you basically have a checklist. I need to do A, B, C, D, and then it's done. Or in every step, if there's error, you go to error, and that's done. But especially the later example, they're basically simplified examples of what we use in the printer. We really want to guarantee safety. And in the end, you can be very confident in the application. Like, we had a lot of bugs, of course, in implementing this printer. A lot of things went wrong, but it never suddenly started printing where we didn't want it. The opposite, yes, it did happen. And we were not happy about it. But at least the end result is safe.
Does anyone have questions?
So somewhere in the beginning, you showed us some blocks for which there were a couple of green blocks, which were in Rust.
Yes.
And then also some off-the-shelf components, which you hinted at that you weren't completely happy with them.
Yes.
Can you say something about why you weren't happy with them, and are you considering also doing it yourself in Rust?
Well, part of it, I thought it was like, it's always good to emphasize like all of it is in Rust, and we have the most problems with that black box. And that is also mostly the reason. It's not that I mean, the off-the-shelf thing, it is probably implemented in C, but that's not the biggest issue we had with it. The biggest issue we had with it is that it is literally a black box. We don't know what it's doing, and the documentation is limited. And for that reason, even though there's always a trade-off, right? If you're making a product, what you want to do, you want to go quickly to the market. So what do? You pick off-the-shelf components where you can. In practice, it's a lot of the time, these off-the-shelf components, they're very good at one thing, but only if you do exactly what the original developer had in mind. If you don't do it and there's no documentation, yes, we have considered doing it in Rust. So far, we're not going to do it, but maybe down the line.
So in the presentation, you showed us a state transition graph, which allows us to better understand what the machine is supposed to do and how it's supposed to operate. At least in my experience, I find that the visual graphs, are a lot, the state transition graph. So I find that these are a lot easier to understand than the actual code, right? It's much more visual, and I can clearly see, oh, there should be a transition from state A to state B or whatever. Specifically in the context of really mission critical code where you want to be really certain about these things, would it not be somehow helpful to combine the visual and easy to understand aspect of actual state transition graphs with your Rust code? Have you tried to investigate would it be possible to somehow embed these sorts of graphs or give some more visual representation to the state machines in your code?
I think you're making a really good point. I have not really investigated it, but I heard one of the other speakers about writing macros and generating a lot of stuff. I can imagine that you can write a pretty nice macro that basically transforms between like these two. If you can annotate this with some kind of macro and generate this, that would be really nice. Right now, you can design this and put it next to the code and go one by one, like check, yes, this one is good, this one is good, this one is good, and then, but yeah.
Or the other way around, where you have the graph and you generate the Rust code from it.
That one would also be interesting, but to me that would be a bigger challenge. But yeah, I would really like to see that.
I have just a very quick remark, but the second half of software systems, we teach about things like this, where you build a graph first and see how you can generate code out of that, which we try to at least address.
Any more questions?
I think that's it. Thanks.